Leaving Earth has never been easy. Every rocket that climbs toward orbit is fighting the same brutal equation. To escape our planet's gravity, a spacecraft must reach roughly 40,000 kilometers an hour. And almost everything about that rocket, its size, its shape, its entire design, exists only to carry enough fuel to hit that number. The payload, the part that actually matters, the astronauts, the satellites, the cargo, ends up being a tiny fraction of the total vehicle. Picture packing for a trip where 96% of your suitcase is gasoline and the remaining sliver is your actual clothes. It is an expensive, wasteful, and fundamentally limited way to reach space, and it puts a hard ceiling on how much humanity can ever send beyond our atmosphere. But there may be a smarter way, one that does not require breakthrough physics, exotic materials, or decades of unproven research. Think about how transportation evolved on Earth. Roads made travel by car practical, rail lines made moving freight efficient, ports turned ocean shipping into a global backbone of trade. Nobody rebuilds the highway from scratch every single time they want to drive somewhere. Yet that is essentially what every rocket launch does. None of these systems eliminated the need for engines, but they dramatically reduced the effort needed to get from one place to another. Space has never had anything like that. Every mission starts from zero, fighting the same fight a rocket fought decades ago. Space infrastructure could change that equation permanently, and one of the most promising forms it could take is remarkably low tech. A cable and a counterweight, known as a tether. The concept behind a tether system, sometimes called a skyhook, is almost deceptively simple. Imagine a long cable, hundreds or even thousands of kilometers in length, stretched out in orbit with a heavy counterweight at one end. If you set this entire structure spinning, something interesting happens. The tip of the cable at the bottom of its rotation slows down relative to the ground below, while the tip at the top of its rotation speeds up dramatically, almost like the far end of a spinning sling, or, if you want the less dignified comparison, a cosmic game of tetherball, where losing means drifting quietly through the void. A spacecraft could rendezvous with the slow-moving lower tip, latch on, and let the tether fling it upward and outward as it completes its rotation. The spacecraft gains a tremendous boost in velocity, essentially for free, borrowed directly from the rotational energy already stored in the system. This is not pure theory. Ultra-strong synthetic fibers already exist today, engineered to survive the immense tension a rotating tether would experience. Engineers have proposed weaving these fibers into a redundant, web-like structure rather than a single strand, so that a stray piece of debris or a micrometeorite impact would sever only a small part of the structure rather than destroying the whole cable. And because a tether in the right orbit would pass over the same region of the planet multiple times a day, spacecraft would have repeated opportunities to catch a ride, turning the system into a kind of recurring shuttle service, rather than a one-time launch. None of this comes without serious engineering challenges. At its lowest point, the tip of a skyhook would be moving through the upper atmosphere at speeds around 12,000 kilometers an hour. Dip the tether too low, and atmospheric friction generates enough heat to threaten the entire structure. So the system has to stay high enough, typically somewhere between 80 and 150 kilometers up, to avoid the thickest part of the atmosphere while still remaining reachable. Specialized spacecraft would need to climb to meet the tether at exactly the right altitude and moment, a far cheaper proposition than accelerating all the way to orbital velocity under rocket power alone, but still no small feat of precision engineering. Catching the tip itself is arguably the hardest part of the whole concept. The rendezvous window might last only 60 to 90 seconds, and during that narrow slice of time, a spacecraft has to locate and connect with a small structure racing overhead at more than 10 times the speed of sound, which engineers would probably describe as a normal Tuesday, and everyone else would describe as absolutely terrifying. One proposed solution involves extending a lightweight capture line, more than a kilometer long, tipped with a small guidance drone that helps steer an incoming vehicle into position before the window closes. There is another problem lurking beneath the surface of this idea. Every time a spacecraft catches the tether and gets flung toward orbit, it draws energy from the system, slightly slowing its rotation. Left unaddressed, a skyhook used repeatedly would gradually lose momentum and eventually become unusable. The elegant solution is to think of the tether less like a simple sling and more like a cosmic piggy bank of orbital energy. Spacecraft arriving from deep space and descending toward Earth can transfer their momentum into the tether as they slow down, effectively making a deposit, while outgoing spacecraft withdraw that same energy as they are flung away. Balance the traffic in both directions, and the system can operate indefinitely with little to no net energy loss. Any small remaining deficit could be corrected using electric or chemical thrusters that nudge the tether back into its proper orbit over time. The more the system gets used, the more efficient and self-sustaining it becomes. The real payoff becomes clear once you imagine a full network rather than a single tether. Picture one Skyhook in orbit around Earth and a second one in orbit around Mars. An outbound tether near Earth could catch a spacecraft in low orbit and hurl it toward Mars at high speed. On arrival, a second tether in Mars orbit would catch the incoming vehicle and gradually slow it down for a safe descent to the surface, all without expending the enormous amounts of propellant a conventional Mars mission would require. The return trip could work the same way in reverse. A vehicle launching from the Martian surface would only need to reach a relatively modest speed through the planet's thin atmosphere before a tether reached down, caught it, and slung it back toward home. The impact on travel time and vehicle design could be dramatic. Instead of the roughly 9 months a conventional rocket trajectory to Mars currently requires, a tether-assisted journey could potentially cut that down to 5 months, or even 3. And because so much of the propulsion burden shifts to the orbital infrastructure rather than the spacecraft itself, the rockets involved could shrink dramatically, potentially requiring somewhere between 80 and 90% less total vehicle mass for the same mission. With that much weight and complexity removed from the equation, there would finally be room to think about passenger comfort in a way that has never been possible in spaceflight, which is a polite way of saying future astronauts might get actual legroom. And this idea does not have to stop at Mars. From Martian orbit, another tether could reach out and fling spacecraft further still toward the asteroid belt. The first mission to a new asteroid would still need traditional rocket power to slow down on arrival, but every mission after that could potentially find a tether waiting, ready to catch an incoming craft and send it home again without burning a drop of fuel. Cheap, repeatable access to asteroids could be transformative, opening the door to mining valuable metals and minerals and delivering them to Martian orbit within weeks of extraction. The most ambitious version of this vision looks toward the moons of Mars. Phobos, the larger of the two, orbits unusually close to the planet, and it is massive enough that spacecraft launches would barely affect its orbit over time, making it an almost ideal anchor point for what engineers sometimes call a super-tether, a structure roughly 6,000 kilometers long. The lower end of such a tether could skim just above the Martian surface, making pickups remarkably easy, while the upper end, moving at tremendous speed, could fling spacecraft outward toward Jupiter and Saturn. The same structure, used in reverse, could also bring the inner solar system closer, offering quick, low-cost trajectories toward Venus and Mercury, worlds rich in solar energy and valuable minerals that have historically been difficult and expensive to reach. Taken together, a network of tethers stretching from Earth to Mars and beyond could form the backbone of a genuinely interplanetary transportation system, one that does not depend on burning enormous quantities of propellant for every single trip. None of the physics involved requires new scientific discoveries. The materials needed already exist in some form today. The distances between planets will always be vast, but with the right infrastructure in place, vast does not have to mean impossibly far.